restriction is the way you turn them into matrices has to satisfy this relationship, which if A times B equals C in your original algebraic structure, when you turn them all into matrices, so H of A is the matrix of A, H of B is the matrix of B, and H of C is the matrix of C. When you turn them all to the matrix, the same multiplication process should work. If A times B equals C, the matrix of A times the matrix of B should equal the matrix of C. It has to follow that rule. And so this has the advantage of turning things into very concrete objects, but the disadvantage a little bit that you might have too much information, but that doesn't necessarily have to be a bad thing. So an example of the representation is the rotations in the plane form a group. I can rotate by 30 degrees and then rotate by 60, so that turns into a rotation of 90. If I rotate by 70 degrees, I can have an inverse, which is rotation by negative 70 degrees. I can compose the rotations, do one after the other. And there's identity, which is just don't rotate it, leave it alone, rotate by 0 degrees. And the representation of this group is actually these matrices, which you might assume if you take a linear algebra. These are the rotation matrices. When you multiply with this, it ends up rotating points on a plane. So it has also a natural action that you can interpret. And these will have the same exact properties as the rotation group. So that's one example. Our examples are a bit weird. So now the Borel representation. The Borel representation is the classic representation on grades. How it's defined is simply, we know what the generators of the grade group are. Generators, as a reminder, is things that when you multiply them together, you can get everything. So everything can be decomposed into generators as product of generators and their inverses. And what you do for this representation is you just take all the generators and assign them a matrix in a systematic fashion. But you have to do it in a way such that all the braid relations are satisfied. So that all those little equations that I wrote up earlier, they must be, my new matrices have to also satisfy them if their predecessors did. So these matrices will do it for the case of 4 strands. Remember, if you have 4 strands, you have 3 generators. Cross the first 2, cross the second 2, cross the third 2. The 3 generators turn into these guys. And notice that the elements of my matrices are polynomials, very simple polynomials. When you multiply them together, you get more complicated polynomials. The inverses, we also allow inverse powers of t. So together with all these guys, we have represented the grade group. Because now we know what the generators turn into, we know what the inverse generators turn into, and they all satisfy the braid relation. So if everything's hunky-dory, A times B equals C implies matrix of A times matrix of B equals matrix of C. And again, notice that they have inverse powers of T. So in general, you're going to have that the Borel matrices, their elements, are what's called Laurent polynomials over the integers. You're going to have polynomials where you have powers of T and powers of T inverse. And the coefficients are always going to be integers. And another weird thing is that the rows of these Borel matrices always add up to 1. If you notice, they do, even to this case. And even when you multiply, that preserves. Consequence of that is that it has an eigenvalue of 1 and an eigenvector of 1, if you know it, of just 1, 1, 1, 1, 1, depending on how many, if it's an m by n matrix, it has a vector of 1, then all 1s. And so if you know what eigenvector and eigenvalue means, then that means something to you. And it was Vaughan-Jones who noticed that because of this, matrices that have this property are usually stochastic. They pop up in stochastic calculus and probability theory, Markov processes. And even though this can't really be thought of probabilistic because you have T's and T inverses, you can still kind of assign to it an analogous idea of a random walk, randomly walking on your grades, and you can maybe fall off or continue. That's how the random walk on the grade works. You have a likelihood of falling, because the polynomial of your likelihood is falling off and continuing. So before we go on, I need to introduce some conventions. This is a positive crossing, which is distinct from a negative crossing. I don't know if you notice what the difference is, but so how can you tell them apart? So the way to tell them apart, it doesn't seem like there should be really any difference, is right-hand rule, kind of from cross products in Calc 3. Place your hand on the upper strand in the direction it's flowing, and then curl your hand towards the bottom strand, so towards the direction the bottom strand is flowing. This points out of the board, so it's positive. Okay? The negative one, I put my hand on the top one in the direction it's flowing, curl towards the bottom one, my finger points into the board, we call that negative. crossing. And that's how you tell them apart. And that's literally what I do when I was working things out. I'm like, what is this? So that's what you have to do. My advisor likes thinking of a screwdriver, and I don't know how he does that, but yeah, everybody has their own way. So now into the limb representation. Remember I said that Logan-Jones noticed Burrell representation has this whole mechanical random walk thing on braids, falling off, staying on things. Lin took this idea and extended it to string links, so he's like, hey, will this work on string links? And it turns out it does. And so his representation, what it does is it uses this table right here that I have to encode the information of walk starting at one node and ending at another. What's the likelihood, quote unquote, the polynomial likelihood of getting starting at one and ending at the other? And the rule is, if you're on a positive crossing, you have a 1 minus t chance of falling, and you have a t chance of continuing. If you're on a negative crossing, you have a 1 minus t inverse chance of falling, and a t inverse chance of continuing. And then, so you can imagine walking on your string lengths, you fall, there's many ways to get from here to there. You could fall, continue, do a whole bunch of stuff. You can loop around, possibly. And that will, when you multiply all those things out, that will be the probability of starting here and ending there along that particular trajectory. And so the ij entry of your matrix is going to be, if you start on the ith source and you end up at the jth node, what is the likelihood of doing this as a polynomial? So I will do an example in a second, but it works for this. Notice, again, the rows sum up to 1, and let's use that random walk interpretation here for the simple braid. This is the positive crossing, by the way. If I start on the first node, the first source, what's the likelihood of getting to the first sink? Well, the only way I can get there is falling off. There's no way I can get there if I don't fall off. So falling was, if you recall, 1 minus t chance. So I fall, 1 minus t. That's the likelihood of getting there. It's the only way to do it. To get to the far away one, the second sink, well, the only way to get there is if I go continuing. So I can pick up a t chance. If I start on the second one, what's the likelihood of getting to the first? I can't fall off. I can only fall off if I'm on an upper strand. I can't do anything with the bottom strand. There's no jumping in this random walk. It's not a random jump. So I can only move forward, and so likelihood 1. And how can I get from the second one to the second one? I can't. Likelihood 0. So that would be it applied to the simple one. So that's really simple. And it, of course, gives the same thing as the Brow representation, because Lin used the idea of the random walk Jones noticed and took it and applied it to strings. So it will always agree for braids, even more complicated braids. Yes?
So you have to get the upper left
odds.
Like probability the upper left represents the probability of getting from the lower left dot to the upper left dot.
Yeah.
And you have to fall off that one, fall in the lower.
Yeah, you have to. And you have to follow the trajectory that the strand is assigned, the orientation. You can't go upstream, you have to always go downstream. Yeah. And what I mean by downstream is you got to follow the arrows. It's like one of those board games. You have to keep going in that direction. Yeah. So, furthermore, so this is a bit surprising, but it's nice, is that it doesn't depend on your choice of diagrams. It shouldn't really, if you're representing the string links, which are equivalent under deformations, just like the braids, and the same goes for tangles. Your choice of diagrams shouldn't make a difference in the final computation. So if I were to compute using Lin's representation, all the likelihoods, 4 by 4 possible likelihoods, for this one and do it for that one, I should get the same thing, and you do. Because these are equivalent, so they give you the same exact matrix. Yes?
But to me, it looks like the one on the right, I could fall off and take the first node on the bottom to
Which one? The fourth source to the fourth sink?
I can take the bottom left source on the right diagram and go anywhere. So on the left diagram, I can only go to the first.
You can go anywhere, pretty much, except the third one. But you have to count up the probability. So I'll do this one. I will show you that that the final probability for going from 1 to 3 is 0.
And what about 1 to 4?
1 to 4 is also 0. It's also 0. I'll show it really quickly.
Can I not cross over?
You can, but you have to sum up I'll show you. So, what's the way to? Let me draw it out. I guess. What's the way to? Okay. So I think this is all. Okay. So you're saying let's start here and get here, right? You're saying I'll get a non-zero probability, right? This is not true. if I go here, I can't do anything here. I go here, I have a choice here, right? I can jump off. Correct? This is one way of getting there. The other way of getting there, the only other way of getting there, is jumping off here, right? There's only two ways of getting there. So, what happens if you have two disjoint options of probability? Then you sum up the probabilities, right? Yes? Two disjoint situations, sum up the probabilities. So what's the probability of starting here, getting there along this trajectory? That probability is going to be, maybe I should use different colors. That probability is the other one. It's going to be, can't do anything here. This crossing is positive, so I get a t, or, well, I go here. I jump off here, that one's actually negative, so I get a t inverse. And, let's see, and then here, I jump off, so, right, this is positive. This is, oh, it is negative. Oh, no, it's fine. It should be fine. Because, let me just see why. Right, okay, let me start this over. I did it wrong. So if I start here, go here, right? Notice I cross here. I forgot about that one. You pick up a t here, right? And then, this is conditional now. Because here I go here, I pick up the following a 1 minus t inverse. Right? For the other case, I just get 1 minus t inverse. 1 minus t, because that one's positive. So this one's positive, this one's negative. T times this gives me t minus 1 plus 1 minus t. Everything cancels. Lin actually proved that this will always happen if you can deform things, that things that should cancel will cancel. And it's kind of magical, but it's true. So, does that convince you? Okay. So, it's an invariance of the braid, really. But Lin extended this to string. So now we can sort of sometimes tell the strings apart. Let's remind ourselves that means that whenever we do Lin on a braid, it will give us the same thing as Bra on a braid. Because Lin is simply an extension of the representation onto a larger world. It uses the same definition, except now kind of extended to string links. Whenever you use it on braids, it's the same exact thing as Bra. So it's a generalization of Bra representation. So let's do another example. Something that's non-trivial, like this one. Not like this one. So this is the fish link. That's what I call it when I name the file. So what we're going to do is we're going to see what happens if we go from here to here. We're going to start walking along. So from 1 to 1, we're only going to compute the 1-1 entry, and the rest I'll just tell you what it is. So from there to there, nothing happens. We don't pick up anything. But if we cross this, we pick up a t, right? Because this is a positive crossing over there. Okay. It's positive. So we picked up a t by crossing it. Now we have another crossing we have to decide on. Well, if we continue, we're going to pick up a t inverse. Okay? So the weight of that path is 1. Now let's do another trajectory. We do this one, again, cross, we pick up a t. But what if we decide to jump off instead of continue? We have to pick up a 1 minus t inverse, because this is actually a negative crossing. Now we're at that decision point again that we went past once before. Yeah? Oh, whenever you're on a positive crossing, all the consequences are positive powers of t. When you are on a negative crossing, all the consequences are negative powers of t. So you get a t for continuing on a positive crossing, you get a t inverse for continuing on a negative crossing. You get a 1 minus t weight for jumping on a positive, and you get a 1 minus t inverse on a negative for jumping. So here, we pick up a t again, right? Just like before. But now, let's escape. Let's finally get to where we want to go. We pick up a t inverse. So notice those last two cancel. When we multiply it all out, we get t minus 1. You can kind of imagine that same deal is going to happen. You're going to start picking up, if you jump a second time instead of just continuing, you would have picked up another 1 minus t inverse. And the t from the original would have stayed. But then the rest of the t's and the t inverses are going to end up canceling.